I'm absolutely thrilled today to have Garth, who's the founder of Panthalassa. I'm super stoked and very fortunate to have been a relatively early investor in Panthalassa. Again, one of these stories where, yeah, that's how we originally met. Very exactly. Not a huge check, but still happy to be there. And with the way this guy is growing, it's going to make a difference. So, Panthalassa, yeah, I'll let him tell a little bit more about that. But they're doing essentially energy and compute at sea, which is very interesting. And then Shrep here, for those of you who don't know, needs no introduction. CTO of Meta for a long time, is probably one of the only people in the room that has actually made the decisions that we're talking about. And it's been really encouraging for me to see how open-minded he is. Who knows? Maybe we'll see a terawatt from Meta coming soon. He now runs his own clean energy investment fund, and I believe is on the board of Panthalassa. Yeah. Beautiful. Okay, gentlemen. So I'd like to start. I mean, I know for both of you guys, some of the things we're talking about here on terrestrial scale and Bitcoin may sound a little crazy. I'd just like to start. How crazy do we sound to you guys right now? Like everything we've talked about so far.
Well, I was going to go first of all, why are you surprised I'm open-minded? I was like trying to figure out, I was like, what does that mean?
Well,
So,
sadly, most people I met at big tech have not been as open minded as the pirates have been so far. But you've got the pirate ethos, which is awesome.
all right. What's funny is because usually I show up with Garth and things, and we first have to define what a gigawatt is, and then have to get people's minds like around what the hell it means to do something in the ocean with power. So like, I feel like we're the normies in a weird conference on this one. I think that the real challenge with all this stuff, I think it was the person from Crusoe who said it right. In my own personal experience, is like the difference between a spreadsheet and the real world is not like one big thing. It's 4,000 little annoying things. Like I can't get a freaking electrician to show up to like wire my thing at the top of the rack. And so like we can't build faster. And that, the 8,000, with thousands of people on site building just the freaking building. And if you've ever seen someone wire a fiber array, it's like a very complicated manual thing, very difficult to automate. Compare wiring a fiber panel to, installing solar panels. Solar panels is like big suction cups, pick up big plate, put down 4 bolts, you're done. I'm very optimistic we're going to automate the crap out of that. Like building data centers is actually quite a difficult thing to do and requires a lot of trades. There's a lot of laws. Like it's just like it's like it resists optimization, even with like highly optimized people working on it. So it's like those physical challenges are there. But at the end of the day, I mean, one of the reasons I'm a believer in Garth is like we get to skip all that crap because we're basically building a ship and then we're throwing it out in the ocean. And that was the non-intuitive thing because sorry, I'm talking your book here, but like, as someone who built stuff on land all the time, when I first heard like, let's just do this in the ocean, I was like, that is a terrible effing idea. It's like, that is a way to make everything 5 times as expensive. Literally an hour on most ships is about $10,000. So anytime you drive a ship anywhere, you're just like your economics go pear-shaped. But you start like looking at what it takes to build one of these things and you do all the comparable work in a data center, you're like, it's actually like less material, less stuff. You're not like generating power in one place, up converting it to high voltage AC, down converting it back. It's like you like generate the power right next to the compute and you use it. And so you just like total part count starts going way down. Assembly is very automated for these things. They're just basically, it's like building a soup can. It's just a big soup can. And you can like bend these things and weld them in very mechanized facilities where we already have the technology. You're buying like literally off the shelf parts. And so it's one of these things it sounds sort of stupid. And then as you poke at it, it looks better and better and better as you go. So I feel like the weird guy in most places I show up because like we can also talk about fusion and other things. This stuff all sounds like very like, yeah, let's just do all of that. So definitely put solar panels every place so there's good solar radiation. Like I'm sort of annoyed as humanity that we tend to just kind of do the same thing over again and do what kind of everyone else is doing. And I think the really interesting opportunities are to like do something a little out there. So sorry, that was a longer like monologue than I think you wanted. I'll shut up.
One quick follow up to that before we jump fully into Panthalassa and what you guys are doing at sea. You made an offhand comment to me, Shrep, that one of the challenges is just kind of a mindset. No one wants to be first. What do you think it's going to take for one of these hyperscalers to say, okay, Crusoe did it, whatever, at the tiny megawatt scale, but like, no, we can do this gigawatt scale?
I mean, my experience in technology in life is sort of like the ChatGPT moment. We built an AI research lab in 2013. I spent a lot of time trying to convince people AI was going to be huge and cool. And like, I mostly failed until like, I was like, try this ChatGPT thing. And I was like, oh, that's super cool. So I think you got to like touch it and feel it and see it in the real world. No fancy presentation or spreadsheet model is going to convince even really smart people that like, oh, this thing's going to work, because they can come up with 60 reasons why it's not going to work, and half of them are halfway right. So I think it's just like my sort of mission in life now is to like prove it by doing it. And so we're gonna have a video feed. You're gonna type, you're gonna be talking to a model with like a live camera feed of one of Garth's units like bobbing in the ocean, generating the tokens back to you. And I'm gonna be like, oh, you're worried about latency over Starlink for the thing that takes you like 10 seconds to type? Like, I don't think that's an issue. So that's where we got to get to with all of these things. So like, I don't know why I'm here exactly, but for everyone in the audience, like,
do any of us
my on planet Earth, but no,
exactly.
my big like
This
encouragement
dimension.
is just fucking go do it. And like, and I think, and I'm honestly prodding a bunch of the hyperscalers to go do some of these crazy things. But I think once someone goes out there and does it, then you immediately flip to, why aren't we doing that? Because everyone else who didn't do it, like, why didn't we do that? And so that's the best way, is to just show it to people, and then everyone's like, that idea is great.
So Garth, tell us about the crazy thing you're proving in the real world right now.
Yeah, well, so hi everyone, Garth Sheldon-Coulson, Panthalassa co-founder. Yeah, the basic idea of the company is go to the middle of the ocean and capture energy there. And, I think a place to start is like, why the hell would you want to do that? Why would you want to go to the middle of the ocean? It turns out that the ocean has these really cool properties that we appreciated some of them at the beginning. And as we go on, we learn more and more of them. But I'll just give you some of them, because I think that it's relevant for people who are coming to solar from first principles, these other things from first principles. One way to think about it is the ocean is our biggest solar collector by far. It's this massive, we're an ocean planet. Sunlight comes from the ocean, hits this thing, mostly turns into thermal energy. That turns into wind. The wind blows and creates these waves over like 20% of the Earth's surface. These waves are like this super, super concentrated solar energy. And it's accumulated there, and it's on 90% of the time in these regions. So it's this giant battery for solar energy that you can just go and sit in, and you can just sit there with a machine that turns out to be much smaller than the equivalent solar panels, and just capture that energy around the clock without the same intermittency constraints. And it can be much, much cheaper. So one of our systems is like $1.50 a watt for a 90% capacity factor, compared to like, the best you can do on land,
Wow.
which is like $6 a watt.
That's crazy.
With all the batteries and all of that included. But then that's not the only thing. The other thing is, okay, all of a sudden you've got the best cooling on the planet, because you're in this giant heat sink. It's like all of the world's thermal mass. It's right across a steel wall from you. So you don't need all the CapEx that's associated with most of the stuff in a data center. You don't need the power transmission, because you're just taking it from like right turbine right here to compute right here. So you mostly eliminate the cost of the data center too. And it turns out that that's like twice the cost of the power. So your cost stack gets reduced enormously just to start. And then you get some of these cool properties like mass producibility, because, water is the best way to move mass around, much better than trucking, much better than train. So if you can be mass producing these systems at a coastal facility, you can be deploying them out into the resource for like no money, bringing them back anytime you want to repair them for like no money. So you can get this circulation going of systems, just like SpaceX rockets going off and coming back. And that's a much better deployment model too, because you don't need to send all the people to the site. You don't need to go build all these massive infrastructure projects on land. So, you can sort of go on. There's even more things than that, but there's these like first principles reasons. And so the big thing that's missing is like, can you make the tech that does all of those things? And so that's what we spent a lot of time doing, and what we have now is a pretty cool system that you can deploy a lot of. But that's the basic idea: go to the middle of the ocean, capture energy, get a bunch of cool properties.
You drop the punchline. How much power is down there?
Oh yeah, it's a big resource. So
Good board memory.
yeah, I mean, it's like, you can easily go get 10, 15 terawatts. There's a lot more than that to
Really?
get. But yeah, it's one of the three, we sort of count there as being like three big resources: solar, nuclear, including fusion, and the oceans, ocean, wind, and wave together. And, because it's the sun that makes the wind, it's the wind that makes the wave. So that's just one big resource. And those three each have multi 10 terawatt potential easily. solar. Anyway, they arguably all have 100 terawatt.
I wish we had the graphic here, because you have this amazing graphic picture of the Earth, and red to green in terms of amount of wind concentrated or wave energy. And you look at this plot, and you basically have the bottom of the Earth with this giant red band, this 10 to 20 terawatts of power, and zero resources consuming it. And then you look at all the places where we're putting wind turbines, and they're all like green. You're just like, we're putting all the stuff where the energy isn't. And like, if we just put it where the energy actually is, your costs and efficiencies get so much better. And Bitcoin is the ultimate transportable compute resource. But AI inference, training is hard because you need big interconnected data centers. AI inference is like easily transportable, and it's an easy way to turn energy into dollars, just like Bitcoin. So I think that like, we're definitely going to do this.
Yeah, and what we're trying to do too is minimize contention with other uses. Like, people were talking earlier about like solar is really great in theory, but there are difficulties in securing the land and stuff like that. But for us, we're going out into this resource where the amount of land, the amount of surface area that we occupy is, 1/100th of what you'd be doing for the equivalent solar. But in addition to that, there's no competing uses. There is no shipping in these regions. There's no fishing. There's no farming. So for every gigawatt we deploy, that's saving a lot of land for farmland, for other uses on land, hopefully saving a lot of like dirty water from fracking and things like that. So, there's lots of good things about doing this if you can get that mass production scheme going.
And something that might appeal to this audience in particular is there's other benefits of being in the high seas. Would that be fair?
That's true. It depends what you're trying to do. I mean, one nice thing about it is it's a global commons by design. The law of the sea says that nations may not establish sovereign jurisdiction there. That's for historical reasons, where I think it turned out that like colonial powers did try to establish sovereign jurisdiction there. But basically what we said was like, look, this is everybody's. Nobody can say you can't be there if you're not touching the seafloor, if you're not emitting bad things. So we can just be there with our self-propelled systems, just like anyone else, just like a ship, just like a sailboat. And that gives us scaling properties that are also pretty different, because you don't need to permit things like, 10 years in advance and all of that.
One thing I'd love to understand is on the cost. Can you give us a sense of what the scaling laws are for your technology, and cost in two cents, like the sort of LCOE? So you gave us like $1 per watt, like the levelized cost of electricity for what you're running this through and what you think that can get to, and also the cost for compute. Because to your point, apples to apples, it's not just who can get the cheapest electron. It's also, to your point, compute or cooling, which is a huge cost of running the data centers as well.
Yeah,
you should talk, and then I'm going to add some thoughts.
Yeah, great. So, So the typical cost stack on land is like all in, if you're doing natural gas, it's like all in maybe $3 to $5 a watt for your power, maybe $10 to $15 a watt for your data center, and then like these days, easily $25 a watt for your chips, maybe more. And this is what Mez was saying before. And so for us, what we do is we take that infrastructure layer, which is like, let's call it $15 a watt. We mostly eliminate the data center part, because we've got the free cooling, we've got the no transmission, all of that stuff. And then we cut the power piece at least in half, probably, basically down to like $2, $1.50 a watt. In LCOE terms, that's like 2 cents per kilowatt hour. We can put some firming in there depending on what the customer wants. We can get our capacity factors up from like 90% to, close to 100% if that's what the customer wants. But we happen to think that most of this stuff will go towards just like dynamic pricing, where it's okay that you're not at 100% capacity factor because you're just modulating the pricing with your availability. But anyway, so that's roughly what it is. And then the other big property that we think is important and what we're trying to achieve is the really rapid dialing up and dialing down of production. If you're building power plants and data centers on land, you have to look at that 4 years, 6 years in advance, because those things take a long time to build. Because what we're doing is just a factory that spews out these things called nodes. We can overbuild the factory. The factory is pretty cheap. We can say, do you want 5 gigawatts this year, maybe 10 gigawatts the year after that? We can dial that up and dial that down for the customer. And that's a huge thing, because they can't always project out what their needs will be. And if we're truly on this exponential, often you'll be underestimating what you need. And so to be ahead of that is also really important. So those are some of the things.
Yeah, I mean, I just like the other thing that we didn't hear in the earlier conversations that are actually really dominant factors in data center development is cooling. Cooling, it's a double bang because it actually costs a lot of capex to build the cooling infrastructure. And then depending on what kind of cooling system you use, it may be inefficient from a power standpoint if you're using dry cooling, or you may use a lot of water if you're using evaporative cooling, which is more energy efficient. And we've seen in Georgia and other local residents are like, yeah, I don't want this data center because it's millions of gallons of water a day. And like water is a true limited sort of resource, fresh, clean water. So, and this sort of system avoids, effectively both of those because and as you move from, when I first built data centers in 2011, they were air cooled. That was the way to get them most efficient with slight evaporative cooling if needed. The power density of the GPUs today is way too high to do air cooling. So you are doing 2-chip water cooling at this point for any of the latest generations. You have a cold plate on the chip. That means you have warm water that I then need to chill to get back to the chip. In a environment like the ocean, you can basically have a sealed box within in box water cooling, and then you're just immersion cooling it in a very cold reservoir, which is the ocean water, which is absolutely amazing. If you had to air cool that, it'd be a disaster. So like it just happens to be perfectly fit for the interval we're in right now. And that is like one of the things that drives down the total system cost because I'm not building a chiller. And I'm not powering that stupid chiller, and it's all the associated stuff. If you've ever walked through a data center, like what the hell, what's that thing? It's like, well, that's the thing that does the thing that does this. Like, there's just so much stuff there. It's not just like a building and servers. And so when you can just shrink that total part count, you end up with like, if you were like designing it in SimCity, you'd be like, oh, this is definitely the way you would do this. You wouldn't build these weird buildings on land.
And people sometimes ask us, well, are you heating up the ocean? And what I say is like, look, actually, all that energy is in the system already. We're just taking it from the waves right there, which we're going to break and dissipate and add their turbulent energy back to the ocean in a little while anyway. And we're just consuming it, and it's not adding any net energy to the system compared to, say, natural gas, where you're taking this chemical out of the ground. That's new energy input, and then the greenhouse gases are adding 100 times that energy input, which is heating up all of the oceans. So it's like we're adding zero, they're adding like astronomical amounts of energy to the oceans through that whole system. So it's sort of win-win we get the best cooling, and it's not adding any net energy to the Earth system.
Sweet. How do you guys think about, the sort of opportunity for training versus inference? Is it possible? I didn't realize 10 to 15 terawatts. That's incredible. Could you get this to a point where you could do, I don't know, one of these like major base model training runs in the ocean? Or is that probably going to stay on land and this is going to be ideal for inference, or both?
Probably ideal for inference and reinforcement learning. We are going to get to large unit sizes, but I don't know that we're going to get to the density of network interconnectivity that they use for the SGD training runs. But where this goes is probably that most of the demand will be inference, reinforcement learning, synthetic data generation, and that kind of stuff. And what we want to be hosting is primarily like the middle tier of hardware in terms of cost. Because if you have if you've got a $40 a watt chip, like please put that in your fancy data center somewhere. Don't have it like bouncing around on the high seas. What we want is the like $10 a watt chips, like just infinite amounts of $10 a watt chips, and that's the thing that pairs best with our platform.
Cool. In general, I guess a question for you guys, kind of zooming out. How sort of like scaling pilled are you guys both? Like when I show a picture of Hans Moravec up here, do you agree we're going to continue on those laws? Like, do you kind of agree? Mez showed some very interesting, yes, we're going to have to use a lot more and maybe it's more linear, but like if we just keep adding the compute, like how close are we to the S curve leveling out?
Shrep can moderate my stance.
You heard it here first.
I think that I'm one of the people who thinks that people don't really understand what's coming. Like to me, the value creation is still marginal, but it's so clear that the value creation will be absolutely enormous. You can come at it from different ways. We actually came at it back in we started in 2016 and 2017. We did what Mez did. We just looked at the exponential curves on compute energy. And we're like, this is a true exponential, like aggregate compute energy consumption. And it's an exponential in spite of Moore's law, which is making the chips more efficient rapidly. And the aggregate energy is going up exponentially despite that. So you've got this crazy exponential coming from value creation, coming from just aggregate amount of demand. And that's continuing. It's still the case. Moore's law is slowing down a little. So the exponential, and then you've got massive value creation from the models. I think you're going to have the agents working with each other, as people said, in these sort of micro economies, trading with each other, solving problems. and yes, you'll need settlement layers for that. It's all going to be really interesting. And there's this mantra. I forget who said it originally, but like everywhere on an exponential, it always feels steep, no matter where you are. And right now, it feels crazy to people who are trying to find energy. But when we look back, this is going to feel like the super flat part of the exponential when you combine the value creation with the Jevons law, stuff and so forth. So I happen to think that the ratio of the input costs will flip. And the chips will become relatively cheaper because that is something that you can mass produce much more easily. That'll go to its marginal cost of production, which is going to be like $5, $6, $7 a watt. And the energy piece will be bid up a lot because you'll be chasing the energy. And that's going to be the hard part.
Peter Thiel was on Meta's board for a long time, so I spent a lot of time with him, and he would always talk to us about how humans don't understand exponentials because nothing in nature runs at you at an exponential acceleration curve. And I think it's totally right. And so I have sort of a more nuanced view, which is I think. And nuance is the wrong word. It sounds like I'm saying smarter than you. I have a different view. Which is like, I'm generally like super bullish on what we're doing. And I think people underestimate what humanity can build in a rough time frame. Like Mez, I don't think showed it in his charts, but if you plot, the first 100 terawatts of solar power, it's the fastest, energy generation source humanity's ever built. The next fastest is actually fission. If you look at the 1960s and you're just like, if we just kept doing what we were doing before 3 Mile Island, you had a curve that looked like this. And so like, we're kind of in this world where people are like, kind of like, we don't know how to build stuff. And I guess it's total, utter just horseshit. And I think we have demand now, which means we have dollars, which means we'll do it. And if you just look at like building solar and building batteries, they just get cheaper, 10, 20% every doubling of capacity size. I'm a little worried about the problem with exponentials. You misunderestimate them here. You also misunderestimate them on the top. And so like batteries, for example, I think, $50, $60 a, kilowatt hour in China right now. Like, I don't know how much lower we can get than that, but like US is already 2x that. So if we just get China's prices, we can still do it. If we just build all the stuff we know how to build at the prices they're at, there's just so much we can do. Like, and building Garth's thing and like building fusion and fission, it's just like, I just get really frustrated with the conservation, efficiency mindset. One other way to think about this is during the Industrial Revolution, we increased per capita energy use by a dramatic amount. We've been reducing per capita energy use, in recent years, and sort of celebrating that on some. And look, I'm trying to do sustainability and climate. Like, I think it's actually backwards. I think we're going to start increasing per capita energy use because we're going to outsource knowledge, e.g., and intelligence into AI agents. And I think that's an effing good thing. And I think we're going to power it with a lot of very clean things. And energy use per capita, everyone's seen these charts over and over again, is like highly correlated with wealth and with prosperity. And so like, I think we should be driving that curve in a different direction. So
welcome home, Shrep. You found your new tribe. It really is crazy to me because I also am a longtime environmentalist, and this whole degrowth mindset is just insane. Because to your point, the faster, and to Mez's point, the faster we drive things down their cost curves, the more abundance we get for everyone, right? And I think that's something that a lot of people miss, is that the sort of positive externalities that Sam was talking about. If we get free energy, the world is a radically different place. So
yeah, I mean, I just I as an investor now look at a lot of things, and I like keep coming back to this annoying same conclusion, which is like, all right, how do we make decarbonized steel good? How do we make it cement? How do we make chemicals? How do we fly in airplanes with sustainable aviation fuel that's the e-based, not bio-based? Like, the answer is always cheap energy. It's like 80% of the input cost of all those things is energy. So it's like, okay, crap, I got to go make that energy, 4x cheaper. And then all that stuff becomes like super easy. It's all totally, we can make fresh water. We could like regreen the Sahara. There's like so many things that humanity could just like, we can just go do. And if we want to do massive carbon removal, it's an energy problem. So first attack the energy problem and get so much of it we don't know what to do with it. And then we're going to start doing some really cool stuff.
And that's why all the distributed energy stuff is so important too, because our thing, but other things too, like every kilowatt hour we take off the grid keeps those things cheap for people. And, that's really important. There could be a sort of dystopian world where energy prices globally get bid up a lot for all the things that humans need to run their biological processes, and that would not be a good thing.
Let's just like think about this for a second. It's like, why would I put the compute in a place that has 110 degree summer day and then try to freaking cool it and bring all the energy to it, rather than put it where the energy is, 10 terawatts of untapped energy where there's nothing else around, no one to care about basically, and I have like an awesome cooling heat sink there, and then use that that precious land for something else that needs to produce something that's local. That data that I'm producing can fly up on Starlink and fly back down in tens of milliseconds. Like, it doesn't need to be close to me. Like, so this is why, like, I'm excited about, we should build tens of terawatts of sort of open ocean power, use it for the compute. I'm making a bet that it'll be one of the more dominant sources of energy for compute in the coming decades. And then we have all this other energy on land to do all the other stuff I'm talking about.
I love to hear it, and I hope it's Panthalassa and as well. I have one last two-part question, and then maybe we all have time for one question from the audience. We'll go a little bit over because this is a pretty cool opportunity. In terms of my two-part question for you guys, one, so I think we all agree the story of humanity is the story of harvesting more energy and the story of harnessing energy to create abundance. I think long-term, I'm curious to hear you guys, if you try and think out to 2050, what does the world look like? Do we get asymptotically free electricity? Are we doing Dyson spheres? What does that look like for humanity? And in the short term, and Shrep, I know you started by saying, well, why was I surprised you're so open-minded? I guess one question I have is like, we're all thinking about the really long term of where free energy goes. But at the same time, I'm also sensitive for, big public companies. Maybe they believe this too. But if, we have a big overbuild in the short run, obviously Wall Street's not going to love that. How do you think about balancing that where everyone's sprinting? We're all trying to get to energy abundance. And yet, if we overspend too much, we find ourselves, in a rough position for both of you guys.
It's not clear to me that we drive the energy costs down on that time frame, like because of what I was saying earlier. I think that there's so many sources of demand, mainly from AI, but also other things that'll be chasing it, that I actually think the average cost goes up for a good amount of time. That's going to drive enormous innovation, which is great, and it's going to be on every company like us, nuclear, fission, geothermal, everyone, to respond to those demand signals and try to create these techs that can keep up with it and drive it back down. So we'll see. It'd be great if it went to zero, but it's not obvious to me that happens on that time frame.
And 2050?
Yeah.
Interesting. Next 5 years are going to be messy. Way over demand on things we don't know how to build quickly. I think that I worry a lot about the grid because it is not a technical problem. It's a societal, political problem, and those problems are just intractable. And so I'm most interested in things that end run around that with technology, which is Garth's project doesn't really give a crap about the grid. So I think we're on one of two paths. I think there is a path where, as humanity, there's enough demand, there's enough investment in a bunch of these things. And it's not one thing, it's Garth, it's fusion, it's fission, it's demand response, it's lots of batteries, lots of solar. And we sort of build out the capacity that people start to see the benefits in tangible ways, like lower, home electricity prices or cleaner communities, and that gives us the license to keep investing in those things. I think we could be on another path, which is the short-term sort of bit up of all of these things gets the average consumer, home energy. When has anyone talked about their energy bill, right? Except for elections, right now. This is an issue for people. It's I get this bill, it's triple what it used to be. Why? That's somebody screwing me. Is a very is the rational response to that. And that is going to create an immense political backlash on all of this stuff unless you can really figure out how to do it. And we need private money, we need government money, we need philanthropic money. This stuff isn't free, but if we can make these things work, this is tens or hundreds of millions of dollars of R&D for each one of these projects, but then unlocks a new, it's a new thing in the tech tree in the video game. So I think if we can get that, if we can protect that for long enough, I think we can have an awesome future where I think of it as, decarbonization to me is sort of our prosperity and lifestyle are completely decoupled from its impact on the planet. So we can do whatever the heck we want, and it's totally cool. And we can still farm, in the Midwest, which is we're not going to be able to do if we do some other things. So
Totally. And one last follow up on that, because we talked about in spot price anarchy, how do you make sure that in the process we all believe where markets are taking us, but that grandma doesn't get $100,000 bill? I actually am very sensitive to that. And this is probably above any of our pay grades to answer, but what do you think is the best way to make sure people are included along the route so that while we're off racing to AGI, there's not a French Revolution in the process?
Well, I think there's a lot of education that needs to happen. The cost of people's energy, especially in California, is so much more about the grid than it is about generation. But that's not the story most people think. It's not obvious to anyone. And And I think that better regulatory, like I think Texas has it more right than everyone else, frankly. Like lower energy prices than the average American in Texas, and they've deployed more solar and battery and wind. And like they didn't have a bad summer this summer, although they did a couple years ago, and that's mostly we think because of batteries. 10% of power from like 6 to 8 p.m. on the Texas grid is freaking batteries discharging that was charged up like at noon. So that's amazing. So I think we need to, and to my earlier point, is like I think we need more of those examples. We need more Panthalassas. We need more batteries discharging on the grid. And you can say, no, 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 no. We can have it like that. It's not a spreadsheet or a presentation. It's like, let me show it to you in person. And then people start to demand, like, wait, why is my local utility continuing to charge me more money to like bury power lines? Like this
sure.
like doesn't make any sense at all. So I do think people are smart when you give them the right data. And I think we're just like not educating people with the constraints. And who wants to know about the grid? I plug my thing and it works. And that's the way humanity should be. It's like, I don't, companies in the early 1900s had a VP of electricity. Like, you don't have that anymore. Like, we're kind of like having that now because it was like this weird exotic thing that you had to worry about. We're kind of like back there. So anyway, longer story.
So I think we have time. We're already over time, but
Sorry,
one question. Yeah. So,
make it a good one.
I know Sid's already asked one. Is there anyone else that hasn't? If not, it's going to go to Sid. So there's a free market for, okay. Oh,
we scared you away. Did you have a question? No, come on. We get his question too. Come on. I made a joke and I put his hand down.
It's kind of wild to me sitting in the audience hearing you guys talk about this stuff. I think I know the answer. Have you heard of hash rate heating? We talk a lot about solar and batteries everywhere. I think there's a third option, which is hash rate heating. You can actually mine Bitcoin and it creates a floor price. And you can, I think where we're going is we're going to have solar panels and batteries in every house and Bitcoin-powered water heaters. So when grandma can take a shower and get paid sats for it, we've got edge load demand response at the edges of the grid. And this is the answer to, we talked about mesh grids. We talked about one power market. I'm actually building the protocol to make this possible where people can trade hash rate shares in real time at a very granular level. So have you guys heard of the heat punk movement?
Yeah. And I think like the analogy I'd use there, this is like, so I came out of tech. And so that, whenever you build a network, anyone understand how networks and IT, a switch, they always have buffers. Meaning if the incoming packet rate exceeds the outgoing line rate, you like hold the packets and you wait and you forward them on so that you're not having to build your networks to your peak data rate, just your average data rate, which is exactly opposite of how we build our grids. We basically build our grids for peak data rate, all the way down to the home. And so if we had some buffering capacity in each demand source in every single home and every, couple of hours worth of battery, I can heat up my water for my shower. Everyone's seen the data. You could cleave off 50% and you get paid for it. So like, this is another thing that I'm pretty excited about, that like the economics we got to figure it all out. And it's complicated because you got to get in everyone's home. But like, you are starting to see some motion in this, that, Base is trying to do it in a different way by installing batteries and then doing demand response and giving people money. There's a couple $100 a year to the average consumer, which is pretty good. So I think that this is another huge lever that we're just not deploying.
Super cool panel. I'm Sid, co-founder, CEO of Liquid Energy. I was nodding along the whole time because you guys speed ran through all the talking points from my company. We also do a distributed compute plus energy and modularized factory produce, except on land with solar and storage.
I'm sorry.
We'll get to that. But I'm curious about your thoughts on inference, economics and demand in the short term. How do you inference also is the economic scale with batching very well. So you get back into large clusters and all that. So how do you deal with that? What's the smallest size cluster you think is going to be viable out in the ocean? And also inference demand, you're pretty much gated by all the demand goes to the big model providers that are all proprietary. There's marginal demand for open source models. So if you go look on Open Router or stuff like that. So yeah, how do you, curious about your thoughts on both?
Yeah, great questions. The degree to which batching is important for the economics really depends on whether you're using super high cost memory or not, because it's all about the memory pooling. And right now it's anyone's guess where we end up in terms of the architectures for, is it megawatt scale NVIDIA clusters with really fancy HBM? Is it much cheaper boards over PCI running LPDDR, and it's like $4 a watt, and you can just have as much of it as you want? Nobody really knows what that'll be in 2035 right now. So it depends. We're trying to make it possible to do both on our platform and be really agnostic to that. But it does have huge ramifications for the economics, for the cost structure, for how much data you need inside and outside your clusters going in and out. So anyway, you know all these things, but we have to be agnostic to it, I think, and be able to design for either. What was the second piece again? Oh yeah. Yeah, I mean, also anyone's guess. Like right now, you want to be working with the big model companies, and we are, for multiple reasons. They've got the best models, they've got big balance sheets, very, very smart people. And then at the same time, you look at papers where, ensembles of small open source models, not even mixture of experts, can be outperforming the biggest models from the best companies on like a large swath of tasks. And it's, free to get the weights, and you can do it yourself. So it's also anyone's guess where I think a big question is whether the model companies can keep their advantage, whether they integrate down into the chip layer in ways that make it really hard to run models on sort of agnostic hardware. That becomes very interesting. But they're doing huge amounts of research that us mere mortals don't completely understand right now. So
I'm surprised you're that qualified on it. Like my bet was very simple, that inference demand is going to overwhelm and is near infinite.
That I agree with.
Okay.
Yeah, that I agree with. The question is whether it's like open source models in like an open distributed market, or whether it's, proprietary models.
Yeah, I can bet best money is probably on that right now. Like, unfortunately, I did release llama on some other things, but the proprietary models are really good right now.
Beautiful. One last very quick thing, since we did talk about payments. I hear one day we could see some Bitcoin mining at sea. Is that something that could be in the works?
We've done Bitcoin mining at sea.
Oh, you've already done it?
Yeah,
already done
on prototypes.
Oh, beautiful.
Now we're on to the next thing.
All right. Well, you heard
that
it here
was like
first.
2 years ago.
But it's coming back though one day.
It depends on the cost structure.
Okay. Beautiful. Wonderful. Can we please get a big round of applause for these guys? Thank you guys.